Math and Beats. In this video, what we're going to do is we're going to talk about a topic called differentials. What are these differentials? Let's see. All right, again, we're going to revisit the linear approximation to a function. Remember, linear approximations give, well, approximations to functions via the tangent line. However, this time, what we're going to be interested in is estimating actual changes in the function's values. So what does that mean? Well, let's first assume that we have a differentiable function, f of x, on an open interval I. So function f of x, nice and differentiable, and let's consider the following graph here. So here is picture. The blue function is y is equal to f of x, and here we have just some particular value of x that we're interested in, and as we can see, we have also drawn the tangent line on the point of the curve of f of x at x. So function, nice and differentiable, and therefore the tangent line exists at x. Now, prior to this, what would have been discussed is discussing the numerical values of the tangent line itself. Now remember, this tangent line in this context we often refer to as L of x for the linear approximation, and that line gave, decent approximate values as long as you're nearby the point of tangency. However, we're going to look at something slightly different here, and that is our goal is to actually estimate the change in the value of the function f of x over an interval, let's call it x to x plus delta x, using that same linear approximation L of x. So change in output values now that we're estimating rather than just the values themselves. So we have a little picture to help us visualize this exact idea. So again, we have the same function f of x drawn. We have its tangent line drawn at x. And as we can see, we've moved out some delta x units away from x, in this case, to the right. And so the distance between x and this other location, x plus delta x, is, well, delta x units, as we've also drawn right above here, right? And then we can see that over this particular interval of x values, the function has changed some amount. What is that amount? Let's call it delta y right there, right? So that's that little piece right there, right? That the function has gone up or down by, or maybe even not changed at all. In this case, it has gone up a little bit. And that change in the output value from x to x plus delta x is the change in the function, which we're going to call delta y here. And that is something we'd like to estimate using our linear approximation. So that's the goal. How do we estimate that delta y? Now, of course, the slope of the tangent line at x is given by dy dx, right? That's been our notation, our Leibniz notation. And remember that though dy dx has various forms you can denote it by, one such form is right down here, and that is that dy dx, the instantaneous rate of change of f at x, is the same as the limit as delta x goes to 0 of the ratio delta y over delta x. And so, you think change in output direction in your numerator, change in input direction in your denominator, and as that change in the input direction gets tinier and tinier and tinier, closer to 0, then this gives us the slope of the tangent line at x for the function f of x. Now, assuming that that limit exists, meaning that, the slope of the tangent line is defined at x, then we could define these two different quantities here, and that is as delta x goes to 0, the limit as delta x goes to 0 of delta y can be thought of as dy, and the limit as delta x goes to 0 of delta x can be thought of as dx. So really what this is saying is the infinitesimal, tiny, itsy bitsy, as small as you can think of, change in the y direction is what we call dy. And that same itsy bitsy, infinitesimal, tiny change in the x direction is what we refer to as dx. That's really what those notations refer to. And so those are their own little things, if you will, and that's part of the topic of this conversation here. Now, if you go back to the picture, the change in the x direction is always delta x, but that's just really the same as dx. So as long as my delta x is super tiny and approaching 0, that's some change in the x direction, and that is not going to change, right? Because x is the independent variable. And so if I make a little tiny change in the x direction like so, here's some delta x, it's really the same as dx. And we'll see a picture here in a moment to help us visualize that as well. And so here is how we define differentials, first of all. The dx, like we were just referring to, is what is called the differential of x. And as we said, it's an arbitrary, tiny, infinitesimal change in the x direction, whereas dy, right down here, is the differential of y, and correspondingly, it's an arbitrary, tiny, infinitesimal change in the y direction. Now, remember, the whole goal here is to somehow estimate delta y, the change in the output direction, but now using the slope of the tangent line at x, dy dx, and that is, well, we're going to estimate using our differential dy in the corresponding y direction. So we want to estimate delta y by using the differential of y, dy. How does that relate to our tangent line at x? Here's a picture. Here's what's going on here. Okay, so let's dissect this. First of all, again, you got the blue function y is f of x. You got the tangent line at x, given by the red line there. And then, just as we had in the prior picture, we have some delta x change from x to x plus delta x some other location. And what else do we have? Well, correspondingly, right here, we have some change in the output direction of the function. The goal is to estimate that using our differential. Now remember, the slope of this tangent line is dy dx, right? So this line, L of x, has slope equal to dy dx, meaning is if I move left or right in the x direction, then correspondingly I'm going to move up or down depending on the function by some dy amount, right? So you think if I move from x to x plus delta x, then the change in that x direction, both on the function and on the tangent line, is the same. We have moved some units in this picture to the right, both delta x or dx, since dx represents the change in the tangent line, and delta x here is just the change in the x direction in general. Now, as I move up and down, my function is going to change by some corresponding amount. That's what we refer to as delta y here, right? That is the change in the function's value. However, in that correspondingly interval of x values, my tangent line at x, L of x here, has changed by something else, right? It has changed right here by dy, whatever that change might be. And so, in general, that change in the output direction of the linear approximation here, the tangent line at x, as we can see, is not going to be, in general, the same as the change in delta y. Now, coincidentally, it could be, but in general, that's not true. And so we should think this change in the y direction of our linearization at x can really give us an approximation to the change of the corresponding function values as we move from x to x plus delta x in the x direction. And that's really the big idea here, is that we can use that change in the y direction of the linear approximation to estimate the change in the actual function's values. And so another application of a derivative. Now, keeping all that in mind, like we just said, when at least we're nearby the x location, right, the point of tangency, then the differential in y should be approximately the same thing as the change in the function's outputs, or delta y here, right? Now, as we move farther away, like in this picture, from this location of tangency, if we're way down there, then it's not going to estimate it very well. Or if we're way down there, not so well. However, if we're nearby this location, right, then my change in my output direction in the function is approximately the same as the change in the output direction of the linear approximation. So if we go back and we just interpret dy dx in terms of differentials, well, we know that dy dx is the same as using the notation f prime of x for the function, using that notation, right? That they mean the same thing, the slope of the tangent line of the function f at x. Using differentials, we can write dy is f prime of x dx. Now, how so? Well, you just start with dy dx is equal to f prime of x, and treating dy and dx as their own arbitrarily tiny infinitesimal change in the corresponding x and y directions, then if I simply multiply both sides of this by dx, then we get the result. Now, when we're dealing with a context that's not this situation, that's not something we normally do. However, when we are approaching the situation using the linear approximation like so, this is something we can do, and hence the differential in y is determined by f prime of x times dx, the slope of the function of f at x times its arbitrarily little tiny change in the x direction. And thus, in general, differentials assume that you got a function f of x and it's differentiable on an open interval where x belongs to that open interval, say I here. Then the change in the output direction, delta y, is the same as the value of the function at x plus delta x minus f of x, right? So here's my function, y is f of x. Here is my location, x. And then if I move out delta x units to some other x, then where we will be at x plus delta x. And the corresponding change here is going to be this amount. And of course, at that location, at the top, that's the value of the function f at x plus delta x. And so if I subtract the value of the function f at x plus delta x and then subtract from that f of x, I get that change, right? That's my delta y, like we saw in the other picture. However, as we've also discussed, since x is the independent variable direction, then delta x is really the same thing as dx. So I could write this as f of x plus dx minus f of x. But that, as we just showed, is approximately dy, right? Delta y is approximately dy, which is f prime of x times dx. So that summarizes the results that we were discussing so far. And so now we'd like to see a couple of examples using this idea, okay? Estimating changes in function values. Let's suppose that we got a situation here in which the length x of some square is measured to be 10 centimeters. So you got some square, you measure it, it's 10 centimeters. But we know that the measurement that we just took could have an error of at most 0.1 centimeters. So, you measure something, there might be a little bit of error involved in that. Let's let a of x represent the area of such a square. The question is, what is the maximal error in calculating the area of such a square? And let's use differentials to approximate this. So, first of all, let's just draw a square, right? Here, I will attempt to draw a square. Not the best square ever. Maybe I'll just make it a little bit longer in this direction, like so. Okay, whatever. Just pretend it's a square. Then this square, we know, is measured to be 10 centimeters on its side, but in general, we're calling each side of the square, say, x, right? That's why we depict it as a of x for the area. So clearly, the area of this square is going to be x squared regardless of what is the side of the square x. And what we measured in particular was it's 10 centimeters long with an error of at most 0.1 centimeters. And our goal is to find the maximal error in using this measurement of 10 centimeters in calculating the area, but we're going to approximate it using differentials. So the goal here, right, just to state it, is to approximate the change in the area, right? What is the maximal area or maximal error in calculating the area using the differential in that corresponding direction, which in this case would be dA, the differential of the area. Now, up here, we know that the derivative of a with respect to x, a prime of x, if you will, is going to be 2x just by using power rule. And so it follows that dA, based on the formulas we were discussing a moment ago, should be a prime of x dx. In this case, that is going to be 2x times dx. Now what we did is our measurement tells us that the measured side, right, x, should be 10 centimeters because that's what we measured it with. But the change in the corresponding direction of x, right, is our error, right? Because so maybe it was 0.1 less than that. Maybe it was 0.1 less or more than that. So maybe it's at most 10.1 centimeters, and maybe at the minimal, it's 9.9 centimeters. We just don't know because we measured it, and we might have some measurement in error. And thus, we should think of our delta x here, some change in that corresponding x direction, as, well, remember, it's the same as dx, and that's going to be at most 0.1. And so if we use that maximal value of delta x, or dx here, as our dx, and plug in x is 10, we can get our maximal error in calculating the area, at least using approximations of the differential. And thus it follows that delta A here, which is approximately dA, and dA we found was 2x dx, using these values that we just talked about, should therefore be 2 times the measurement, 10 centimeters, times the error, the maximal error, that is, in measuring the sides, 0.1 centimeters, giving us 2 square centimeters. So if I have a maximal error of at most 0.1 centimeters here in measuring the side of the square, the approximate maximal amount of error associated with calculating the area would be 2 square centimeters. And so there's an example of using differentials. One question we might ask is that a lot of error? Or is that a little amount of error? We don't know because we just have these numbers. So it brings up the topic of what is called relative error. If I could spell it, relative error. And so relative error is just saying exactly what we were just asking is, how much error really is this relative to our measurement? Well, notice that 0.1 centimeters is a 1% error in measurement, say, calculation of measuring the actual side of the square. Now, how do I know that? Because if I take the 0.1 centimeters and I divide it by the actual measurement, 0.1 centimeters over 10 centimeters, that's the same as 1 over 100, which of course is 1%. So really, in general, if we want to talk about relative error, we just take the corresponding change in that direction that we're going, say delta x in this case, over x, or as we can see, it's also the same as dx over x. Now, that's telling us we have a maximal of 1% error in measuring the side of the square here as assumed in the problem. But what about the area, right? What about the area? Well, it follows that the relative error in the area, well, that's going to be delta A over A, right? That should be approximated by dA over A. We found that dA was 2 square centimeters. And in fact, if you plug in x is equal to 10 into the area, remember, A of x is x squared. So if I plug my x into that formula, I would get 10 squared square centimeters, which gives us a 2 over 100, which is equal to a 2%. And so what that's telling us is, in this situation, if we have a 1% error in measurement of the side of the square, what that will result in is a maximal amount of error of 2% in the calculation of the area. So knowing how much error you have is actually quite efficient, because if you have too much error, maybe bad things happen. Let's do another one to finish this video, just so we get the idea down completely, hopefully. Let's say in this situation that the radius of some spherical ball bearing is measured to be 24 centimeters and a maximal possible error in measurement of 0.06 centimeters. The question is, what is the approximate maximal error in using the measurement to calculate the ball's volume? And again, we're going to practice by using differentials to approximate this amount of error. So you have some spherical ball bearing like so, and here's the radius of that spherical ball bearing. Somehow we measured that spherical ball bearing's radius to be 24 centimeters, and we know there's a maximum possible error associated with this measurement of 0.06 centimeters. So our goal in this situation, right, which is similar to the last one, but it's a little bit different, right, is to approximate the change in the volume now, say V for volume, once again using our differential dV. But we need some things, right? We know that the volume of such a sphere, let's call it V of R here because it depends on the radius. We know that the volume of a sphere is 4/3 pi r cubed. And that tells us that the derivative of the volume with respect to its radius is going to be 4 pi r squared. We need that because we're going to use dV to approximate this delta V. We also know that in this particular situation, R was measured to be 24 centimeters, right? That's our measurement. And we also know that delta R, which will be the same as dr, since that's the change in the independent variable's direction, is at most 0.06, right? That's the maximal possible error in measurement. And thus, we can approximate delta V here by using our differential dV. So delta V should be approximately dV, which is V prime of R dr. Using the formulas, that's a 4 pi r squared times dr. And now using the values stated right there above, if we plug those into this formula, it follows that in this situation, using those, we get a 4 times pi times a 24 squared times the maximal possible error in measurement, which is a 0.06, right? And in this case, multiply it out. What do you get? Press some buttons. Beep, boop, bop, boop, boop, boop. 3,456 456 divided by 25 times pi, and even pressing more buttons, boopity boop, you get 434.29 approximately cubic centimeters. So there's our maximal possible error being estimated using the differential in this particular case. Again, you ask the question, well, is that a lot? Is that a lot of error that I expect in my volume when using this measurement? Possible error. Well, let's talk about the relative error again. The relative error in this case for the actual measurement, so let's just say for the measurement of the radius, what's that going to be? Well, similar to that square one, that's going to be equal to our change in our r direction, delta r, over the actual numerical value of the measurement r, or if you prefer dr over r. And then again, this is the maximal, right? So if you get our values that we use, that's 0.06 over 24, and simplifying gives 1 over 400, which is the same as 0.0025, and thus our maximal error in measurement is 0.25%, right? That is the maximal relative error in measurement of the radius, which is, not too big. It's pretty tiny, less than the square problem. And so what does it tell us about our relative error in the volume measurement? Well, that would be delta V over V, right? So here's our relative error of the volume using these same calculations, which is going to be approximated by dV over V. Now, we already found dV above, 3,456 pi over 25. And then the volume is by plugging in the measurement, which was 24 centimeters, into the formula for the sphere's volume, which is a 4/3 pi times 24 cubed here. And boopity bop, press the buttons. This ends up being 0.75%. And so what that tells us is a maximal error in the radius of 0.25% results in a maximal error in the volume of 0.75%. And so there's a couple examples we just looked at in actually using differentials to approximate the change in the output direction. We used a square and a sphere to help us see some examples of this. But another big takeaway, of course, from this video is that what is a differential and how can it be used to help us approximate change in the output direction of some function. So that's it for the differentials video here, at least differentials for single variable functions. And it's Math and Beats, and I'm out.